So far, we've covered the first two major chapters in physics, kinematics and forces. In this video, we will look at the next major concept, work. In this course, we've seen several instances where an object feels multiple forces but doesn't move. That's because for an object to move, it has to feel an unbalanced force. If a force actually moves an object, then we say it has done work on the object. Work is the practical impact of a force. It measures how a force tangibly changes the position of an object. In other words, it measures the displacement caused by a particular force. We measure work as follows. We need two pieces of information, the force acting on an object and the displacement of the object. You'll immediately notice that both these quantities are vectors. They have both size and direction. For our purposes, we will express both of these vectors in polar notation, that is, size and angle relative to positive x. Take the size of the specific force that's acting on the object. Multiply by the size of the displacement of the object. Then multiply that by the cosine of the difference in their angles. That yields the work. It is extremely important to notice that work is a very unique quantity in all the physics we've done so far, because it is a scalar, not a vector. It is one of the very few quantities we've seen so far that has no direction. There are two other things I'd like to point out. First, because work is a scalar, it does not have the vector sign written on top of it. This is a way of making sure that we don't confuse between weight, which is a force, which is a vector, and work. Weight is symbolized with a capital W with a vector sign. Work never has a vector sign. Because work is calculated as a force multiplied by a displacement, the units of work are always in newtons times meters. But it gets a little awkward saying newtons times meters over and over again. So instead, we have a different unit that we use to stand in for newtons times meters. We call it the joule. 1 joule of work means 1 newton's worth of force pushed an object over a distance of 1 meter. Just like mathematicians, physicists love shorthand. For instance, we can write the mathematical expression 4 times 4 times 4 as 4 to the third power. These are two different ways of writing the same thing. This calculation that we just saw, size of the first vector times size of the second vector times cosine of the difference of their angles, is often written in short form like this. The two ways of writing this equation mean the same thing. This operation is called the dot product of the two vectors. Now, let's apply this operation and the concept of work to different examples. Let's look at a simple case. Here, a 5 Newton force is applied to a box. The force is pointed in the positive x direction, so its orientation is 0 degrees. The object displaces 2 meters in the positive x direction. The orientation of the displacement vector is also 0 degrees. We can calculate the work using the equation we used earlier. Work is the dot product of force and displacement, which in turn equals the size of the force multiplied by the size of the displacement multiplied by the cosine of the angle between them. Substitute the values of force and displacement into this equation. The force had a magnitude of 5 newtons, and the displacement had a magnitude of 2 meters. Both the force and the displacement are oriented at 0 degrees. The work is easily calculated. 5 newtons times 2 meters times the cosine of 0 minus 0 yields 10 joules of work. Now, what if the force was not aligned with the displacement? Suppose the force vector is oriented at 30 degrees above the horizontal. The work would now be calculated like this. The displacement is oriented at 0 degrees, but this time the force is oriented at 30 degrees. Simplifying, the work is now equal to 5 newtons times 2 meters times the cosine of negative 30 degrees. That works out to only 8.66 joules of work. So the greater the angle between the force and the displacement, the less work the force actually does. At this point, you're probably wondering if there's such a thing as negative work. The answer is a resounding yes. For instance, suppose you lift an object that has a weight of 30 newtons a distance of 1.5 meters. The weight force is pointed downwards, which means its orientation is 270 degrees. The object's displacement is 1.5 meters upwards, which means that the orientation of this vector is 90 degrees. Substituting the values into the equation for weight, we end up taking the cosine of negative 180 degrees, which is negative 1. So the work done by the weight force is negative. A negative work always occurs when the force acting on an object points opposite the direction of motion. Obviously, if an object doesn't move, its displacement is 0, so the work done by the forces acting on it is also 0. But consider this situation. A 20 Newton object is carried at a constant height over a distance of 3 meters. The weight vector has a size of 20 newtons and is oriented at 270 degrees. The displacement has a magnitude of 3 meters and is oriented at 0 degrees. The work is equal to 20 newtons times 3 meters times the cosine of 0 minus 270. But the cosine of negative 270 is 0, so the work done by the weight force is also 0. Whenever a force is perpendicular to the displacement, that force is doing 0 work. This can be seen in circular motion too. The moon moves around the Earth in a roughly circular orbit. The motion of the moon is always tangential to that circle. However, the force that it feels from the Earth is the centripetal gravitational pull from the Earth. The force, in this case, is perpendicular to the direction of motion. In fact, it's always perpendicular to the direction of motion. So in circular motion, there is no work done. One other quantity we regularly see is power. Power is the rate at which work is done. For instance, if you run up a flight of stairs, you do the same amount of work as if you walked up that flight of stairs. But when you ran, you performed the work more quickly. We say your power expenditure was greater. Power is calculated as work divided by time. For instance, if you do 10 joules of work over 4 seconds, the amount of work done is 2.5 joules per second. Again, it's a little cumbersome to keep saying joules per second, so we'll use the unit watts. 1 watt is 1 joule per second. Be careful not to confuse the capital W for watt with the capital W for work. You run into watts all the time. When you use a 50-watt light bulb in your kitchen, that means it's performing work at the rate of 50 joules per second. Every electric appliance and every electric bill that you read makes reference to watts. In this video, we were introduced to the concept of work. In the next video, we will explore the related concept of energy.